Dear participants and research scholars, a warm good evening to everyone for the third day of this ATAL AICT sponsored FDP, Redefining Innovation, AI and ML for Industry 5.0. For today's session, we have with us Dr. Priyan Kumar, who is an assistant professor in the Department of Data Science at the University of North Texas, USA, with over 8 years of academic and research experience across India, South Korea, United Kingdom, and USA. He is recognized among the top 2% of the world's scientists by the Stanford University for the 4 consecutive years. He holds a PhD degree in the information technology from VIT India, specializing in IoT frameworks for healthcare. His expertise spans biodata analytics, cloud computing, IoT, and cybersecurity. And he has contributed extensively through high impact journal publications, books, and conference presentations. Dr. Kumar also serves on editorial board of reputed IEEE and Springer journals and has delivered keynote talks at prestigious international conferences, making him a highly accomplished academic and globally recognized researcher. We are on behalf of Department of ECE, Government College of Engineering, Salem, we are very pleased to invite you for this session, sir. Thank you.
Thanks for such a warm welcome, sir. Can you hear me?
Sir, you are audible, sir.
Yeah, thank you, sir. Dear participants, good evening. Myself, Dr. Priyan. I working as an assistant professor in the Department of Data Science from the University of North Texas. So we'll start off this our topic. Our topic is about human-centric AI robot. Let me share my screen over here. Can you able to see my screen?
Yes, sir. Yes.
Yeah, thank you, sir. So myself, Dr. Priyan Kumar. I'm working as an assistant professor. So we kickstart our discussion. So this is going to be my outline of my presentation today. So we'll start what is meant by about human-centric AI. So how well it has been used in various aspects of our real-world examples, and our human-centric AI principles, followed by how it has been interacting with our humans in our day-to-day life, and AI in collaborative environments. And after that, we'll talk about how well this human AI is safety and ethics is going to be, and as well as we'll have some kind of a case study with some kind of examples, and in future how well it's going to be useful in our day-to-day life. And finally, we'll have some conclusion. This is going to be our outline of my presentation. So this presentation is for human-centric AI, where we'll be talking about it ensures the technology is designed around human needs and the values, as well as the safety. So the cobots is nothing but in short we'll be calling it as collaborative robots, where and all we are going to be applicable in our real world examples, or like manufacturing use cases, that is of use cases, manufacturing, healthcare, logistics, and various services. And cobots are being a perfect example of this, as they are robots made to collaborate with the people rather than to replace them. So when it comes to human-centric AI, the traditional industry robots are powerful but as well as it's been dangerous, and it's quite often working in isolation. And as well as a human-centric AI, it ensures that robots are safe and reliable and trustworthy partners. So this approach emphasizes the usability, ethical design, and mutual understanding between humans as well as the machines. So where and all this cobots will be useful is, as you see here, the principles of a human-centric AI is transparency and trustworthiness. We have to uh, believe the machine. So after that, the ethical responsibility and the adaptability. What are the collaborative robots are nothing but the cobots are like are robots specifically designed to work alongside the humans. So the major principles relies on this four different aspects that is mentioned over here. That is of transparency, trustworthiness, and ethical responsibility and adaptability. Why human-centric paradigm over here is the human-centric AI shifts the goal of robotics from replacing the humans to assisting them. The cobots as well as embody by this by keeping human in the loop for whatever the daily decision making that we are going to have. The aim is to enhance the productivity and safety while respecting the human judgment and control. So that's the main agenda or goal that we can say. So it has to work alongside on our day-to-day life. And also it should be trust, as I mentioned, it should be trust and safety, whatever the task that we are allocating to that particular cobots. So the key features of our cobots or the human robot interaction, how we are going to make it over here is the cobots are
आपका टीवी आपका
going to be built.
खाना खाता तो
Sorry, is anyone is asking
No,
questions
no, no,
or
sir. I will be muting the participants, sir. Just a moment,
okay.
please.
So this cobots
Sir, you can unmute. Sorry, we're muting all participants.
uh,
Sir, it's
is
audible now.
that okay?
Audible. Yeah,
Okay.
audible.
So this cobots are built with the unique features as I told. These safety mechanisms like force sensors, adaptability to different tasks, and the ease of programming through demonstrations. These features will make us more accessible to small, medium industries as we have various scales of industries in our India like MSME compared to our traditional robots. So where and all it will be helpful like modes of speeches like hand gestures. You can interact with your robots like using your NLP languages and gestures like different gestures that you are going to have and gaze. These are all the things that we are going to have. And the main goal is we have to seamlessly provide information or communication to that particular machine with our natural gestures or communications. So how we are going to have this is human-centric AI research on key principles like transparency. That is nothing but a clear decision and fairness and accountability on how human remain responsible for that particular thing that we are going to have in instructions and trustworthiness. And this makes ensures that the AI works ethically and as well as it aligns with the human values. So HRI is nothing but a human robot interaction. So what you are going to have is human input that it can comes in a different format as we have seen, like hand gestures, yes, or communications from various sources. And after that, we are going to give that input to our machine, that is of AI perception. Followed by that, we are going to have some kind of a decision making, and then we'll be having for the whatever the input that we have given, followed by that respective whatever the instruction followed by that. Say for example, if we are asking into that machine to take a particular cloth or a fruit from a table, so will be depending on that process to happen, and then let's see the machine whether it's particularly following that instruction or not. And based upon that, we'll be getting some kind of a human feedback from the machine. So this cobots rely on AI for perception and vision system to recognize objects and people gestures recognition for natural communication and voice recognition for spoken commands. So these capabilities make the interaction smooth and human friendly. Cognitive and emotional aspects of human robot interaction will make them feel more comfort, workload, and emotional responsible or majorly plays a vital role in this part of these aspects of human robot interaction. So why it helps the cobots to make a real-time decision about a task like a resource allocation and safety. For instance, in a factory, that collaborative environment, cobots decides when to assist worker by tightening the screws after the human places a part, ensuring the teamwork and the efficiency. So when you are assume that you are in some kind of a car manufacturing company, so as an employee, it will be helpful for you to when you have to make the body to screw the particular part. So it plays a vital role. So the human robot interaction will be an effective collaboration requires intuitive interfaces. So this makes more cobots achieve through this voice and control processes and gestures. So this effective collaboration requires, as I mentioned earlier, computer vision. Computer vision plays a vital role since it will be taking the input of, as we have seen, the Tesla cars or whatever the automated cars. So it will be having a various camera visions through that, whether the any obstacles is coming on that way or not, we can be able to see, and we have to move in that particular direction or not. Those decision making will be happening through the computer vision. So moving on to the NLP. So this NLP is natural language processing will be giving the text for the input and a speech. So the effective collaboration and cobots achieve this through voice gestures and augmented reality or video reality tools. This natural forms communication reduce the barriers, as well as it makes the cobots feel more like a partners than the machines. So we can say the missions are clearly like we can feel like an another human is working alongside to make our job ease. So the perception and sensing is nothing but in manufacturing is leading field for a collaborative environment adoption. They perform like a welding, assembly, and packaging, working alongside humans on production lines. This reduces the fatigue for our workers and increases the output. So, a decision making and expansibility. So, in healthcare, cobots assist surgeons with a precise operation and support rehabilitation exercises, and even aid elderly care by helping patients with the mobility. So, and also it reduces the workload, and as we have seen, it also, what to say, it improve the accuracy in the treatment. So it will be also in a transparency, and we can trust the humans in order to make the decisions. So the predictive AI will be like for a human ear motion is anticipates the human actions to avoid collisions and assist effectively. So as we have seen in the computer vision based cars, where there will be like will be having a car where will be mission followed by that manufacturing companies. It will be helpful for the system to make their decisions. So in healthcare, as we have seen, the Cobots assist the surgeons with the predictive in order to make the decisions to properly. So if you see, so in healthcare and medicine, the predictive AI models that forecast the disease for treatment outcomes of these individuals and for behavioral predictions, the systems, the human actions like habits or preferences to predict the future behavior, like as we have seen the regular model like shopping, learning, and decision making. And in workplace or performance, the AI tools that anticipate the productivity, skill gaps, and career trajectories. For personal assistance, the AI will be predicting what the person might need next, like smart reminders or proactive scheduling, even emotional state tracking. Ethics philosophy, thinking how AI predicting human actions changes autonomy, free will be there for social dynamics. This so the major architecture, as we have seen in the previous examples, so where we'll be having some kind of input sensor. After that, we'll be having an processing AI model. So in which we'll be having an input from the user. So after that, what you're going to have is the cobots are increasingly used in various other sectors, like as we have seen in that even in the academics, they are using it for education, for teaching robots and AI concepts in a safe environment. So in research labs, they assist with the hands-on experience to the students. So in logistics, the cobots handle picking, sorting, and transportation and warehouse. So the base of all this, what to say, applications relies on how we are going to give the input. So that's what we are going to have. So the basic architecture that we are going to have over here is will be at first will be giving some kind of an input to the users, sorry, input to the system. So for that, how we are going to have is perception layer will be there for sensing all those data collections for through the cameras like RGB and the depth value. So after that, we'll be having cognition layer in which coordination layer will be predicting what human collaborators is trying to do, and then will be as well as they will be having context awareness. It will be modeling workspace safety zones and task requirements, and will be as well as will be having a task planning in which will be having an reinforcement learning or rule-based technique logic to decide the robots of next action. And then thirdly, we'll be having like a collaboration part where we'll be having some kind of an interaction and adoption method. in which motion planning, whatever the smooth trajectory generation that avoids the collision while staying the while staying efficient, and in which it will be scattered into divided into three parts, that is of human robot interaction, that is HRI, natural gestures, and adaptive learning, whatever the cobot learns from the demonstrations, learning from human feedback and or imitation learn. And then we'll be having the control layer for execution and safety. That is comes in a feedback loop. We'll be having a low level control and safety mechanisms and compliance control and so that's and in safety human centric robots we'll be following safety standards, that is of standard ISO model, that is of 10218. It's a standard one. It's a benchmark one. So whatever the robots that we are going to have, it follows the same standards that you are going to have. ISO standards, it's a key standard. It's preferably general safety requirements for industrial robots and robot systems. It covers like installation and operation and integration into like kind of various workplaces. So ISO it also requires a safety rated monitored stop. It's a hand guiding and a safe speed and safe generation monitoring, power and force limiting. And all. So why it important for cobot AI is it's almost AI driven cobot must follow this comply on this to ensure this ISO standard for human safety in various shared workspaces. This AI system for perception planning and control should always respect force or torque limits and safe distances defined by ISO standards. And this ISO provides the framework for certification so robots can legally deploy. To this safety bubble concept. In this safety bubble concept, what you'll be having over here is so in robots, it will be operating on dynamic environment like various since it works on workspaces. So as we see, green is safe, yellow and red. So the majorly it's placed around like our traffic signals, where we'll be having a dynamic 3D zone around a robot that ensures that humans are always safe at a distance. So if a human enters into the bubble, the robot slows down or stops. It means that they are in a safe zone. So by using the sensors or like a cameras or depth sensors or like safety scanners, so it follows like whether the person is going to coming for in their way or not. So how it is working is the outer bubble, that warning zone, human detected. If a human is detecting, the robot will be slowing down. The inner bubble will be having in a protective zone. Human is too close and robot stops immediately. It should not even move in a single inch. So the safe re-entry. The robot resumes when the human leaves the zone. So the safe re-entry zone is nothing but a green so that they can move from one place to another place if the person is not there. And if it is in a yellow zone, they should be cautioned and they should not. It's like a nothing but an outer bubble. Human is detected and it should slow down. And red means it's an inner bubble. The humans are too close to them and the robot should stop immediately. Examples of this safety bubble that we can say is for factory cobots, like a safety laser scanners create a 360-degree safety bubbles. And for mobile robots, this AMR or AGV moving bubble adjust to the direction or the speed of travel. And ethics that you will be having over here is it place with respect to our privacy, will be having absolute priority of cobots must never harm humans, and it should follow the whatever the ISO standards, and it should be always in the safe zone. So the ethical design is nothing but it should equal the redundant safety checks and fail-safe modes and transparency in the risk. So the autonomy versus control that we can say over here is meaningful human oversight is an ethical principle, and in order to avoid it, they should follow some kind of a black box decisions. The human operators must remain in control of critical functions. So the privacy and the data use that we can able to say over here is the cobots often use cameras, microphones, and sensor in shared spaces, raises privacy concerns about surveillance at workplaces or homes. So the ethical practices that we can that should be equal over here is clearing the policies on data collection and storage and various other accesses that is given to the cobots. And fairness that on aspects we can say is AI driven cobots decision making must not show bias against humans. The ethical AI is mean to be having a diverse training data sets and continuous validation. And trust and transparency that we can rely on this cobots we can say is workers should understand how the cobots prevent to operate on the explainable AI. Trust comes with the predictability, reliability, and honest and about limitations. The next is building trust that we can say over here is building trust. Cobots is always an questionable since it's been getting the input from the users. Accumulators like lightweight back-driven motors, sensors, and safety control mechanisms in low-level control and compliance control and the AI in cognitive layer in which we'll be having a four different tasks it needs to be having and a human robot interaction and the development tools we'll be having in a ROS that is of robot operating system. It's kind of a middleware for our cobot software. And as you see, Casebo is like a simulation and testing environment where the cobots will be always will be tested, as well as if you can use a machine learning frameworks in which a TensorFlow and PyTorch for AI model can be used over here. So the case study that we will be having over here is manufacturing. So the manufacturing company where we'll be having over here is the various mechanisms it has been followed in the for whatever the automotive elements that we'll be having. So assume that we have like a mid-size automotive parts manufacturer, and the main use case over here is workers had to perform the repetitive task like screw fastening, quality inspection, and machine tending. So there will be having a tiring and error prone, and sometimes even it's an unsafe. So the main objective over here or a goal for an employee is to improve the productivity and worker safety without replacing the human workers. So as well as it reduce the humans in assisting the workers, and it reduce the fatigue of an employee, those who are working in that field of study. So the healthcare we can talk about over here is, so assume that we are having going to have a surgery over here, like an setting up in a very large urban hospital, where the problem arises will be having a nurses who are overworked with a repetitive and non-medical task like lifting patients and moving supplies from here and there and disinfecting the rooms. The time they should spend on direct patient care. So the goal over here is using the cobots to support staff and improve the efficiency and maintain the dignity and safety of the patients who are ill. So the patient supports will be given over here by lifting and repositioning the patients without any making them injury further. And the logistics they will be by having the patients in the chair from moving from one place to another within the safety bubbles. And the sanitation and the sterilization process will also be carried with the cobots. So in the logistics, what we can have over here is so the Amazon and the DHL couriers are for packing shelf movement from one place to another. So the large e-commerce fulfillment center where the problem will be having like a worker spending long hours of walking, lifting and sorting packages. So again, the problem of fatigue and a slow fulfillment and the error prompts will be happening over here is how we can overcome by having this is by having a cobots by speeding up the order process and reducing the injuries and optimizing the inventory flow. So the picking and sorting will be again it will be using the stationary cobot arm, picked items from bins and sorted them for packaging. So vision items, identified items are of different shapes and sizes. If you ask them to pick an 10 biscuits, so based upon the sizes, the packets will be arranged and clustered together. So if you ask them to arrange the food items in a separate shelf and the non-eatable items on the other hand, it will be again it will be going to have the same thing. So the challenges that we'll be having over here is it will be having in a four different environment that is of balancing autonomy and human control, cyber security and privacy. Since we are going to give the information in the form of NLP and various other gestures, trust and acceptance, and uh, cost and standardization. So it ensures the cobots don't harm any humans in the shared workspaces and difficulty in maintaining the dynamic safety bubbles since in a cluttered or fast changing environments, the hardware wear and tear, the risk of unexpected failures will be happening over here. So the building of trust workers may hesitate to collaborate closely. Communication barriers will again be happening over here. And balancing robot autonomy versus human control will be also been happening over here. And technical limitations, as you see, perception limitation like computer vision struggles in poor lighting or with a transparent shiny objects. And grippers and manipulation that we can see over here is like handling irregular or whether it's a fragile material or a small item, it still hold it with an iron arm. So there is an always a risk of having that system or a machine. It's in a different feeling of having the machine in a working environment. And adaptability will be in a questionable over here, like a retreating cobots for a new task will be a time consuming. And integration within this cobots will always be in the legacy manufacturing lines or hospitals may not be ready to use this kinds of human-centric robots. And futures in future directions, we can use it in emotional intelligence cobots, smarter perceptions for making our advanced computer vision, and humans intention recognition for predicting what worker plans to do next, and the use of generative AI for adaptive task planning and dialogue-based human robot interaction, and dynamic safety bubbles that adjust the real time based upon human posture and movement. And as well as it develops the soft robots, compliant arms, grippers, and improving the explainable AI so workers can understand the cobot decision makings, and for learning of multi-human and multi population of people will be working over here. And AR VR integration, as we have seen in multi-human and multi-robot framework, it will be difficult for environment mapping like a shared world, people like object zones and task, and human state tracking like posture, location, and workload intention, and robot state sharing. So this are like a questionable over here. And for different positions that you will be having over here is robot state sharing and the sensor fusion. Again, it will be an questionable over here. Combining task or LIDA or wearables with IoT will be an questionable over here. Coordination and decision making will also be a difficult challenges that you will be having in the future. So the conclusion we can say over here is the human-centric AI ensures the cobots on the safety environment. So it represents the major shift from traditional automation towards a human-centered robot where machines and people share the same workspace safely. They bring the clear benefits and reduced worker fatigue, improved safety, and higher productivity, as well as the greater flexibility in industry like manufacturing and healthcare, as we have discussed on the logistics. However, in cobots also face the challenges of ensuring the safety and trust. And to overcome this technical limitations in perception and adaptability, and managing the cost and addressing ethical concerns like a job replacement and privacy and other fairness of this framework. So the compliance with an international standards, that is of ISO standards, is critical for guaranteeing safety and responsible deployment. The future of cobots lies in being smarter, safer, and more adaptive, integrating AI for perception, predicting, and decision making while respecting human dignity, autonomy, and values. True success comes not from replacing humans, but from augmenting human capabilities, fostering collaboration, and creating work environments where humans and robots operate as a trusted teammates. So the cobots are transforming work by enabling safe and flexible human-robot collaboration, and they improve the productivity and safety while supporting, not replacing the human workers. Challenges remain safety, adaptability, cost, and various other ethics. But with the standards like ISO, advancement in AI are set to become a trusted teammates across industries. And to shift the focus from humans to human-centric robots, enhance the safety, efficiency, flexibility, and across the industries, while challenges remain in the safety adaptability. So it also gives you an ethics, past compliances. The future lies in smart and safer. This thing. So any discussions that we can have over here? If you have any doubts, you can ask. So as I mentioned over here, the challenges will also be there in the future if you are having it in a human-centric environment. So it plays on why we are going to have in this thing, uh, safety and trust, maintaining the real time safe zones when humans move unpredictability. So building worker trust in cobots and decision and actions will be unavoidable. Avoiding over reliance, and humans must stay alert and not assume cobots are infallible. Human-robot interaction will be also been a challenging thing. Natural communications like speed, gestures, and AR often fail in a noisy or complex spaces. And transparency workers needs to understand why a cobot acts in a certain way, managing a multi-robot teamwork without a confusion. Ergonomics of work design will also be a challenging thing. Like poorly designed cobot interaction can increase a human stress instead of reducing it. Workers may feel less of autonomy if a cobots dictate workflows. So anyone will get irritated if a machine is teaching you something unethical. Need to align a cobot actions with like human rhythms and comfort. And ethical and social concerns over here is job security fears, resistance to adoption to this new environment, and risk of reducing human dignity in sensitive domains, and privacy risk from covert sensors of collecting human data, adaptability and learning. Humans improve easily, cobots struggle with the unexpected challenges. Continuous learning must be safe and the supervised environment. So personalization to different human workers is still limited. So the resistance from workers due to cost or culture or in different habits. Lack of training programs for workers to become the cobot supervisors, and integrating cobots into legacy environment is also been challenging. So the main picture relies on how we are going to trust this environment. And since if you are even if you follow the basic ISO standards, it will be questionable. So the conclusion we can say over here is the human-centric AI should be safe and secure, whatever the task that we are giving over here. And it should rely not only on a safe and secure environment, it should be on a within the limit it should be having. And in the future, the cobots represent the paradigm shift from automation that replaces the what to say humans to systems with us humans workers. This provide the clear benefits of improved safety, efficiency, and flexibility and worker well-being across industries like manufacturing, healthcare, and various other industries. And the key challenges remain, as we have seen, the different challenges that you will be having over here is trust, adaptability, ethics, and organized organizational acceptance. Even if you follow the ISO standards that we have seen, it advances in AI and are helping to address them. The future of cobots lies in a smarter, safer, and human-centric environment. Thank you.
Thank you very much, sir, for your presentation. I request the participants, if you have any doubts, you can put it in the chat box or you can ask your queries now. We will take a break and we'll be continuing the session by 7:30. Okay, maybe after some time we'll be starting again.
Sir,
Yes.
sir, the next session will be carried out my scholar, sir.
Okay.
His name
Fine,
is
sir. Fine.
Ashok.
Fine.
Okay. So participants, if you have any doubts, you can drop me a mail also mentioned in the slides.
Okay. Thank you, sir. Thank you very much.
Okay. Thank you. Thank you, students. Thank you.
Recording in progress.
Uh, uh, Dear participants, welcome you all for the session 6 of the ATAL online 6-day faculty development program on redefining innovation, AI and ML for Industry 5.0. And the session 6 will be dealing with the topic predictive maintenance using ML in smart manufacturing. So the session is yours. You can continue.
Good evening to all. I hope my voice is audible.
Yes, sir. It's audible, sir. Yes.
Yes, thank you, sir. The topic that we are going to see in this session is how we can do predictive maintenance in machine learning. Okay, so first of all, I will give overall introduction about what is Industry 4.0, what has been done previously, and now how those things are being managed. So previously, what happens is there will be industry. Industry will produce some products, and what happens is in industry will have their departments. Individual departments will take care of each production. Okay, and suppose if we cannot guarantee that the industry will produce enough products in the long term. Okay, so in between, what happens is due to some machine failures or some other external issues, the production will be affected. So what approach they will do is they will be using the traditional approach, which is called as a repair after failure approach. So that is once the failure has been detected, the production will be stopped and then the repair process will start. And once the repair process is successful, and the production will resume again. And what the problem in this traditional approach is, in small industry means it is okay. But in large industry, what happens is a product has to be delivered to from department A to department B or from one industry to another industry. So in that case, what happens is the entire supply chain will be affected. So to prevent this one, efficient approaches, once a failure has been detected, the cost is very more. So that is before a failure is detected. Okay, we can predict, okay, this machine can be failure at this many days. So before that one, how we can introduce some maintenance or some work so that the failure will stop. Okay, we can provide some alternate also. We can introduce some new machines in the production, or to reduce some the speed, we can reduce some speed, or other adjustments we can do. Okay, so this is the process of predictive maintenance. Okay, so this predictive maintenance will is a part of Industry 4.0, and Industry 4.0 doesn't have this predictive maintenance alone. That is from this process, okay, this predictive maintenance process, we have supply chain optimization, digital twin, cybersecurity in industrial systems. So all these concepts comes under Industry 4.0. Okay, so what the outcome of this predictive maintenance? The outcome of this predictive maintenance is we can able to determine whether when a machine will fail. Okay, we can tell this machine will fail today or tomorrow, like that. Or in these circumstances, the machine will fail if temperature is very high, or some other external or internal issues, this machine may fail. So like this, we can able to tell why the machine fails. Also, we can able to calculate how many days this machine will go without maintenance. That is called as remaining useful life. Okay, we will, in short, we will call as RUL. Okay, this RUL tells that, for example, RUL is 5 days. Then we can say that this machine will run for 5 days without any maintenance. So after 5 days, some caution has to be made so that this interruption cannot be, we can prevent this interruption. Okay, so how this predictive maintenance is done usually? Okay, so how this predictive maintenance is done is, in industry, there will be many machines. Okay, so each machine will be connected to various sensors. This sensors will read some information. For example, what is the running speed of this particular machine, or what is the temperature of this machine, or how much electricity is flowing inside the machine. So like this, lots of data this sensors will be monitoring. Okay, there will be multiple sensors for one machine also, and the sensors will keep on collecting the information, and this sensor will send this information to a centralized place. Okay, it may be cloud or a local storage also. Okay, and then what happens is we will be executing some machine learning models which will read this information, and then we can tell that this particular model will model means machine. Okay, so this particular machine will have 5 days of lifetime, or this machine is about to go into maintenance. So like this, we will be able to tell using the machine learning. So in this session, what I am planning to do is, after explaining this, I will show a practical way of developing a machine learning model from some data sets. Okay. Okay. So now, before that, how this data is collected, that we have to understand. Okay, the data will be connected, as I told you before. There will be m number of machines in the industry, and each machine will be connected to some sensors, sensor 1, sensor 2, sensor 3, like that. It is, we can have how many data we want, we can have. And these sensors will try to capture the information at various times. So we can say T1, T2, T3, like this, we can say lots of times. Okay. So for example, let us say 7 o'clock. Okay. So in 7 o'clock, machine 1 is having this much temperature. And finally, the last one is very important, that is time to failure. So how this information will be captured is, before we are migrating from the traditional to this predictive maintenance. Okay, so we need one intermediate stage. So that intermediate stage is nothing but data collection stage. Okay, so this stage is done by experts in that particular industry. Okay, so what that experts will do is, okay, I'll give you an example. Let us take 5 different machines a day: machine 1, machine 2, machine 3, machine 4, machine 5. Okay, and each machine is associated with some sensors, some 5 sensor or 6 sensor. Okay, so what happens is, at time T1, okay, at time T1, maybe 7 o'clock, one person will come, and for one machine, this 5 sensors, what value it is being given, that will be recorded. Okay, and at time 2, maybe 7.5 or 7.10. Again, these 5 sensors, what value they are giving. So that will be recorded. Okay, and then what happens is this machine at one point of time will go into failure. Okay, so what they will do is, so what date that machine is going to failure, that they will be noting. Okay, suppose the machine is going in 50 days. Then we can say that at the time in machine 1, if sensor 1, sensor 2 data is x1, x2, x1 and y1, then this machine 1 will go in failure in 50 days. Okay, so that is one data. So likewise of data, these people will gather. Only after gathering all this information, this data will be given to machine learning model, and then machine learning model will tell us what to do there. Okay. Okay, so first, what we will do is there is a data set. Okay, so it is called as machine failure prediction data set. Okay, so it is having lots of features. Okay, so these features comes from various sensors. Okay, the description of this is given. Maybe we give the link also to you after the end of the session. And what we will be doing is we will be doing two different uh, Sorry, there was a connection issue. So we'll continue. Just a second, I will
Sir, slide is not
start
visible.
sharing.
You can share the screen, sir, again. 1 minute, sir. I will make you as co-host. Okay. Yes, sir. You can share now. Thank you.
Yes, I share. Okay, fine. Okay, guys. So see here. So first, let me import the data set. So step by step, I will do so that it is easy for you to follow on. Okay. So the data set will be imported like this. Read underscore CSV. And then, okay, so this is the information of the data set. So first, we'll be seeing how these values have been arrived at this particular data set. So you can see this rotational speed, torque. So all this information comes from different sensors taken at a different point of time. And this final column, okay, final feature, which tells that this particular, okay, if these values are there, this particular machine has been running or it comes into failure. So that is what this is determining. We will check how many values are there in this particular failure thing. So you can do that with a value count function. So you can see there are two values. One is 0 and 1. And this 0 corresponds to whether the model is failed. So 1 means the model is machine is running successfully. Okay, so now this particular thing we have to predict. Okay, we have to predict. So for that, what we are going to do is we are going to the stages of machine learning. I hope everyone knows. Anyway, I will summarize. Okay, so what generally we'll do is we will divide this data set into two parts. One is training and another one is testing, where this training data set is used by the model to understand the relationship between all the variables. Okay, it will tell whether if rotation speed is this much and all other features are this much, then the model will run or the machine will go into failure. So like this, some lots of relationship will be understood using this training data set. And then once the model has been learned all the relationship, we have to test whether how well our model has been learned. Okay, so that is being done by testing data set. Okay, we'll pass the testing data set after the model has been learned completely. And then we will be checking whether the output of testing data set matches with the output of the model that is predicting. Okay, and if these two values are equal, then we can say the relationship has been learned correctly, or we have to fine tune the model more. Okay, so that is the thing that we're going to see in this particular thing. Okay, so the first step is we have to divide the data set into input and output. Okay, so we call it as dependent and independent features. So that is first X is independent features. So which is nothing but we are going to read all the rows and all the columns except the last one. Okay, so that is we are going to read all the rows and all the columns except the last one. And then we'll convert that into numpy array. That's why we are putting dot values. Then similarly, y is equal to df.ilog and all the rows and the last column alone. So in Python, we can say the last column has -1 dot values. Okay, so now let us see what is the output of x. So this is the x values, which is nothing but this information. Okay, so except the failure column, all other columns are being given to X. Okay, and similarly, we will see what is the value of Y. So this is the value of Y, which is nothing but the last column. Okay, last column values. So now let us make two different data sets, training data set and testing data set. So that is done by so this is the library that is used. We will divide that into various data sets like this. Okay, so we are going to pass X and Y, and then training size will be 80%. Okay, so this we can change based upon that. It doesn't mean that only 80% we have to do. And then we will put random state as 0 to ensure that we all get the same output. Okay. So once this is run, I will show you the contents of each thing. So this is X train. Okay, so which is a sub data set. Okay, so this X is the whole data set. So from this randomly 80% of data we are taking and we are placing in this X train, right? And similarly, I will be showing other values. This 80%, so left of the 20% will be saved in X test. Okay, and same thing goes for Y. Y train contain 80% of the Y value, and remaining 20% is being placed in Y test. Okay, so now if you recall how the machine learning works, we'll be passing the training data set alone in the process of training, and then we will do the evaluation process using the testing data set. So that is the thing that we are going to do. And before that, if you observe one more thing we have to do, that is each feature is having in different scales. Okay, so I will show you what is the scales and all. See here, so the data set name is df. So df.columns. So these are the various columns present. Okay, columns present, and for each column let us see what is the range of the values. So we can, okay, so loop into like this, and then df of, so what happens here is, so we are going to iterate over each feature, and we are going to test whether what is the minimum value, what is the maximum value present in that one. And you can see each feature is having different ranges. Okay, so this first column, the minimum value is 1168, maximum is 2076, and similarly this is different, this is different, and all these are same. Okay, so now generally what happens is, when before training, when you give all this data with different ranges, okay, so the machine learning model struggles to identify correct relationship. Okay, for example, I will tell you, if one value change in rotation speed is different than one value changed in this TWF. Okay, so TWF is, one value is the maximum value. From 0, if you plus 1, it goes to maximum value. But in this rotation speed, it is not like that. If you increase plus 1, still it remains in the minimum range only. Okay, so like this, this is the problem that occurs in training process. Okay, so before going to training process, we have to ensure that all the columns are in the same range. Okay, so how we can do that one? How we can do that one is, in sklearn there is a library called a standard scalar, so which will accept these columns and it will convert that into standard ranges. Okay, so for that I will use in pre-processing, there is a function called a standard scalar. So let us create object for that standard scalar. Okay, so here this x, this, okay, so we are passing here x train, x test. So this one we will be resolving. Okay, so x train is equal to sc dot fit underscore transform. Okay, and then this goes like this. So now what is the meaning of this particular line is, so this fit underscore transform is two functions. One is fit function, another one is transform function. Okay, fit function, what it does is for each and every column, it will find what is the minimum value, what is the maximum value, so that it will keep in the memory. Okay, and transform, what happens is, so here the real mathematics is being done. Okay, so the mathematics is, so we'll have x minus max minus x divided by so like this, some formula. Okay, this is one formula, or some other normalization we can do. So in some other normalization, what happens is, we'll be dividing with the maximum value, and then we will be multiplying that to 100. So like this, so some lots of formulas are there. Okay, so using that formula, what happens is all the values will be in the same range. Okay, so now as I told you, x train, we are using fit underscore transform. So fit function is used to read the minimum maximum values, and then it transforms each and every column into standard values. Okay, and then one more thing we are having given testing data set. So the testing data set, now we should not call sc.fit transform. We have to call only sc.transform. Okay, so why? Because what is the reason is, already we have recorded the minimum maximum values for each and every column. Okay, so this x train and x test are a subsets of the original data frame. Okay, so already we have measured what is the minimum maximum. So once again, we no need to measure it again. Okay, so that's why we are calling only transform function. No need to call fit again. So once you done this execution, so now you can see. Okay, so you can see this values will be, all the values will be from 0 to -1 to +1 only. Okay, but it is not present here. You can see this is 1.55, this is 4.28. So like this it is coming. So this particular thing, it ensures that all the values now are between -1 to +1. Okay, so now we have reached a point where all the columns in our data set is in the same range. Okay, now next one. Okay, so next one, what we are going to do is, we are going to pass this into our machine learning model. Okay, so how we can do this particular thing? Let us create maybe two machine learning models we will create. So first one is, we will be creating a decision tree classifier, and then we will be creating a KNN classifier. Okay, so we'll be creating objects for this. dt is equal to decision tree classifier, and KNN equal to K neighbor classifier. Okay, so now two machine learning models we are going to use. Then what we are going to do? Okay, then what we are going to do is, we are going to start the training process. Okay, so maybe if you are confused, I will write down the steps for you. So the first step, okay, the first step is, we have to divide the data set into X and Y, where X is the input, Y is the output. Okay, so in our case, input is the inputs from the various sensors, and output is whether the machine is failed or not. Okay, so that's what we have done here. this for all these columns. Okay, so all these columns are input. The last column is output. So that one we have done using these two things. Okay, so next step is, after doing this, what we have to do is we have to divide the data set into two parts. Okay, two unequal parts or equal parts, it's up to you. So one is called as training and another one is called as testing. Okay, so this training is used by the model to understand the relationship. Okay, and this testing is used to, okay, so it is used to evaluate the model, right? So this is the second step. So third step, this is an optional step. So this is required only when the values of the column of all columns are in different ranges. Okay, so we can apply any standardization or normalization procedures. So next one, we have to create a model and pass a training data set. Okay, next. So here, after this, what happens is the model will start to learn. Okay, so once the model learns successfully, we will test the model using this data set. Okay, so this testing data set we have divided, right? So using testing data set, and then we can print the accuracy. We can see how well the model has understood. So this process only we are going to do. So let us, since we are having two models, I will start a for loop for I comma j in zip. So first model is KNN, and second model is decision tree, and then we'll be having the names of this model. Okay, so this is just to print. Okay, it is not, we can give any name. So we will have KNN and then decision tree. Okay, so now this step we are going to do the fourth step. Okay, we are going to do the fourth step, that is I dot to ensure the training process, we have to use the fit function. This fit function is same as we saw here. Okay, so in standard scalar, this fit will test what is the minimum maximum values for each and every column. But in machine learning, this fit, what it does is it will try to understand the relationship between the various models. Okay, so here you have to pass the training data set. Okay, so here you have to pass the training data set, that is the first one. Okay, so X train and Y train. Okay, so this is the fourth step, and this once this completes, what happens is the model will understand all the relationship. Okay, so next what we are going to do is we are going to test how well our model is predicting. Okay, so we'll be having one more variable y predict, which is equal to I dot predict. Okay, so I dot predict. This time we are going to pass the testing data set. Okay, the fifth step. Now we are going to do the fifth step. So that is we are going to pass the testing data set. Okay, so testing data set x underscore test we are passing. Now what we have to do is, so we are having one more thing, y underscore test. Okay, so this y underscore test is the original, okay, original result. Okay, and this y underscore predict. Okay, so this one is the result of the model. Okay, so that is what our model is giving the output, that is stored in y predict. And what should be the output? It is y test. So these two we have to compare. If y test is equal to y predict, then our model is successfully learned all the relationship. And if it is not, okay, if some values are mismatched, means then we have some metrics for that. For example, false negative or false positive. So it depends. Okay, so this one we are going to test. So before that, so let me import some libraries. So matrix, import, accuracy score, precision score, recall score, and F1 score. So 4 metrics we will use. Okay. So first we'll print what is the model. Okay. So model is nothing but J. Okay. So model is J. So this is the values of model. In first iteration, it is KNN. Second iteration, it is decision tree. Okay. So next we will print the accuracy. Okay, so accuracy. So first one we have to pass what is the real output. Okay, so real output is y underscore test. That is the real output. Second one is what output that our model is giving. Okay, our model is giving y predict. So this is nothing but accuracy. Maybe we can give accuracy is equal to so like this also. So which makes our output more readable. Similarly, we will follow the steps for the recall, precision, and F1. Okay, so here you have to change. So this should be recall, and this should be precision, and finally this should be F1. So let us see how the model is coming. Okay, so for KNN, we are getting accuracy of 95%, and decision tree 95.38, that is KNN. For decision tree, we are getting 95.75. So that is decision tree somewhat more than KNN. If you want, you can include still more classifiers also. Maybe I will include SVM. Okay, so import SVM also. So let us import SVM is equal to, so like this, we will add SVM here. Okay. So for SVM, we are getting somewhat lesser accuracy. Okay, 93% only we are getting. Maybe if you fine tune this SVM, which is due to lack of time, I'm not showing the fine tune process. Okay, but fine tuning SVM, we can get more than this KNN. Okay, we can get around 97 or something. Okay, so this is the training process. Okay, so now comes actual our question, the predictive maintenance. Okay, so now this process is completed. Okay, so now we are going to see whether our model is going to predict the failure or not. Okay, see here I will show you. Now assume, okay, this is very important. This is where our particular thing is there. Okay, so the data, okay, so data from the sensor, for example, rotation speed is 1555. Okay, and next value is, for example, 41.2. Next value is maybe I will give 2. Next is 0. Next is 1. Next is 1. Next is 0. Okay, let me check the number of values. 1, 2. Okay. So now my question is, now we have done all the machine learning training process. Okay, so now one machine is there. Okay, one machine is there, and the sensor is giving these values. Okay, 1555, 41.2. So all these values. Now we are going to tell that whether this machine will go into failure or it will not go into failure. Okay, so that we have to check. Okay, so how we can do that one? Okay, after developing model. So this is the final thing we have to do. Okay, maybe I will give it here for your reference. Okay, so now what we have to do is this value I am going to pass to our machine learning model. Okay, so I cannot pass this value directly. Why? Because here, why I cannot do is here we have normalized the input values. Okay, so this values also should be normalized. So how we can normalize this? SC dot. Here again you should not use fit transform. here you have to use just a transform to this data. Now, if you print this data, you can see this original values have been changed to this one. This is the what is this one is this is the range in which the machine learning model learns. Okay, so from this the range we have converted into this value. Okay, so how this value comes is based upon this fit function. Okay, this fit function. Okay, now this value I will pass. Okay, I will pass this value to all our model. Maybe I'll put it here. Okay, so now this value has to be passed in the machine learning model, and we have to tell that machine is being um, it is going to get into failure or not. Okay, that is what we are going to find now. Okay, so how we can do that one is so let me put like this: the machine output of, so the model name is J. Okay, so is, so here what I am going to do is I am going to call the model dot predict of data. Okay, so this data is nothing but transform the data. Okay, so now let us execute this, and you can see KNN. Okay, as far as KNN is concerned, the data that we pass here. Okay, so this output is 1. 1 means, it means that the machine will not go into failure. Okay, the machine will continue. But however, the decision tree and SVM are predicting differently. Okay, so it is predicting as 0. Okay, SVM also is predicting 1 only. Decision tree is predicting 0. Okay, so that means the decision tree is predicting that this particular model will come into failure. Okay, so how we can resolve this? Okay, one model is giving one output, second model is giving a different output. So what is the conclusion at the end? Okay, so here only we will be coming into one concept called as ensemble. Okay, so ensemble model. If you are using multiple machine learning models, we cannot guarantee that all the machine learning models will give the same output. Okay, like the example that we saw now. Okay, there is high possibility that each machine learning model will give different outputs. Okay, to avoid this one only, there is a ensembling model. Okay, so in ensembling model, lots of types are there. Maybe we can go for voting. Okay, so voting, we can go for hard voting or soft voting like this, or we can go for staking. Okay, so like this, lots of ensemble methods are there. Okay, so any one method we can apply and we can come into conclusion. Okay, I hope the first project is being understood by all. Okay, if you are having any doubt, you can ask me now before starting to the second project. Yes, any doubt is there? Okay, fine. So the first project talks about whether the machine will go into failure or not. Okay, so that is the thing that we have found. So second project, what we will do is, given one machine, in how many days this machine will go into failure. Okay, so we know whether this machine will go into failure or not. That is the first one. Then if goes into failure means when it will go to failure, whether it will go today, tomorrow, or after 10 days or after 1 month. So that we don't. Okay, so for example, if this value, okay, if this value is 1, we no need to worry, because 1 means the machine is running perfectly. Okay, so we are not going to worry about that. When we are going to worry is when the output is 0. Okay, so the model has predicted that this machine will go into failure. But when it will go to failure, whether it will go to failure in 10 days or 1 month or 1 year, that we don't. Okay, now how to predict that one? So that is, we have to jump from classification process to regression process. Okay, so far what we have done is classifier approach. Okay, classifier approach, we know that machine is working or it will go to failure at some. Okay, then when it goes to failure, so for that, we need to have to convert this process into regression based one. Okay, and for converting that to regression based one, as I told you, this field, okay, so that is, okay, here if you see the last column, it is only 0 or 1. So instead of 0 or 1, we have to change this field to how many days this particular machine will run. For example, if this is the value, this machine will work for 10 days or work for 50 days or work for 30 days. So like this individual values we have to fill instead of this 0 or 1. Okay, so this stage is taken care of this particular data collection stage. Okay, so we'll be using one more data set which satisfies the condition that I told you, which is called as in NASA. What happened is lots of jet engines are there, right? So they have used lots of sensors for this jet engines, and they have predicted in how many days that this particular jet engine will go into failure. Okay, so this one, if you see, some lots of data are there. Okay, lots of data are there, and this one, okay, so RUL, if you remember RUL is, RUL tells about how much remaining lifetime is there for one particular data. Okay, so given, okay, for example, given these values, we can say that it will execute for 91 days. So like this. So this is the thing. Okay, so this lots of pre-processing has to be done in this data set. Due to time constraint, I have done this pre-processing already. Okay, already, and I will show you how this data set looks after pre-processing. So this is the data set. Okay, this is the data set. So here, if you observe, these columns are there. Okay, so these columns represent values from various sensors, and the final column tells in how much days this particular engine will work correctly. Okay, so far there are lots of values are there. So now we are going to do the same. Okay, how we can do that one? So first process is very simple. We have to copy the data set. Okay, so maybe, so this is project 2. Okay, project 2 data set is pd.8_CSV. So let me zoom my screen so that you will be able to see correctly. Okay. So this is the data set. Okay, so this is the data set that we are going to work on. Okay, and the process is same. Okay, we are going to divide into input outputs, and then divide that into two parts: training data set, testing data set. and already it is been normalized only. Okay, already it's been normalized. So the thing is, I will start. Okay, so X is nothing but df dot ilog of all the columns and all the rows and all the columns except the last one. Okay, convert that to numpy array, and then again all the rows and the last column. Okay, so X, this is the value of X, and this is the value of Y. Okay, that is X is the information we get from various sensors, and Y is nothing but in how much how many days are pending for this particular machine for next maintenance. Okay, so next what we have to do is we have to divide that into two parts. Okay, so one is training and another one is testing. Okay, we'll go with same 80 percentage and random state is 0. Okay, and let us test. Okay, so this is some random 80 percentage of this X, and the remaining 20 percentage is placed in test data set. Okay, so likewise, if you go Y, the 20 percentage is this, and 80% will be saved in Y underscore train. Okay, fine. Now, as I told you, in this project, we are not going to predict whether the machine is going to fail or not, but instead of that, one step ahead we are going, and we are going to tell in how many days this particular machine will go into maintenance or failure. Okay. So for that, as I told you, we have to go for regression. So sklearn, we'll be using linear regression for this purpose. Okay, and I will create an object for linear regression. So the first step is to train this machine learning model. Okay, train this machine learning model using fit function. Now our model is successfully fitted. And now let us test. Okay, so let us test by predict is equal to LR dot predict. Here we are going to pass the X test. Okay, we are going to pass the X test. Now let us see what is the values of Y predict. So these are the values of Y predict. That means for the first case, okay, for this value, the machine will go into maintenance in 124 days. Okay, and for this value, the sensors are giving this value, then our machine learning model will go into maintenance in 34 days. So this is the interpretation that we can do. Okay, even you can pass your own values also. So instead of this value, you assume that, okay, you assume that this is, okay, 170. Okay, so like this, you can change some values if you want. So this is 2, and this one is, so some random values I'm giving. So if the sensors are giving this value, okay, now what, in how many days this, if these values are there, in how many days this machine will go into failure. So to do that, okay, so we have to pass all these values into our machine learning model. Okay, pass all the values into our machine learning model. Okay, so it is giving -20. That means our model using this data, the thing, okay, the machine will not go into maintenance in the near future. Okay, so that is not, we are not going to worry. So actually, Y -20 will not come usually. because of some random data I have given. That's why this answer is there. Okay, so if you give correct answer, you will be getting some positive number like this. 45, 97, 34, 90, like this, some positive number you will be getting. This number represents how many days we can trust this particular vision. Okay, so now as we saw in the previous project, okay, these models we have trained and we have made use of this metrics to test whether how much trust we can do. Okay, for example, I will tell if the KNN model accuracy is just 0.1, and if it is giving machine, this machine is successful, it will not going to failure. That means we cannot trust that model because the accuracy is very low. Okay, accuracy is only 10%. Then what is the meaning? The answer that it is giving, we can trust that only 10%. But this one is not like that. Okay, this one is, we are telling 95%, we are confident that KNN is giving 1. Okay, so likewise, regression, we cannot have accuracy score, precision score like that. For regression, we are having one more matrix. Okay, so that matrix is called as R2 score. Okay, and mean absolute error. Okay, or mean squared error. So these metrics we can use. Okay, we can use these metrics. And so let me print the R2 score. So the same thing, okay. So what should be the output? What should be the output and what output we got? Okay, so we got this output. Similarly, print of mean squared error. Okay, so what is the real output and what output that we got? So this is the value. Okay, 0.8 means somewhat we can trust. Okay, we can trust the model. And this is the mean square error approach. Okay, so I will end my session now, and I will open for any queries you have.
Yes, sir. Thank you for the session. Sir, I have a query. Sir,
Yes, sir.
yes, sir. Can you shed some light on this overfit and underfit, and why such thing is happening, and how it can be avoided in machine learning?
Yes, sir. Sir, actually, when you give some data, overfit, underfit occurs in two different situations. For example, there are 3 cases. Okay, so you are giving some data to machine learning model for training. When all the relationship are being captured successfully, then our model is fine. Okay, we'll be getting accuracy like a 95, like we got earlier. Okay, 95, 96 and all. And but in majority of the scenario, when the relationship is not being captured successfully, then there is a problem with the model. Okay, so one is overfit. So overfit means what happens is actually we are dividing the data set into 2 types. Okay, so one is training and testing, as I explained. The machine learning model by hearts the input and output. Okay, for example, in our case, I will give you a practical example. When we are handling classes to students, okay, we will be giving some list of questions. Okay, so what most of the students will do is they will just by heart, this question, this answer, this question, this answer, this they will by heart. But in exam time, slight modification if we give also, they cannot able to recall. Why? Because they have not understood the subject. They have just by-hearted the concept. Okay, this is called as overfit. In overfit, what happens is the training data set will be by-hearted by the model, and no relationship has been found. So, what conclusion is, the training accuracy will be very high. For example, 99.5, 99.7 like this. But the testing accuracy will be very, very low. We cannot even accept that one. Maybe 30% or 45% like this. So this much deviation in training data set accuracy will be very high. In testing one, the accuracy will be very low. Okay, so this scenario is called as overfitting. Okay, so how we can avoid overfitting is there are some approaches. For example, first one, the data is what we give here.
Okay.
Okay, so here I will call. Yeah, here. Okay. So in this line, what happens is we are going to divide testing data into the split is 80%. That means 80% of the values will go into training. Okay, 20% will go into test. So this one you can modify. Instead of 80%, you can reduce that to 60% or 50% like that. Okay. And also, instead of train test with other methods also is there. For example, K-fold learning is there, stratified learning is there. So like this, lots of approaches are there. So this ensure that different data comes into machine learning, and if you do all this process and still overfitting occurs, then you have to change the data. That means the way in which you capture the data is some mistakes are there. Okay, we have to change the data. And underfitting, when you go, it is quite opposite to overfitting.
Sir, one small clarification I need. Sir, so that means based on the test accuracy, if the training accuracy is very high, test accuracy is very low. From that, that may be the one of the reason due to overfit. Am I right, sir? That's what I can infer.
Yes, sir. No, overfitting is that one, sir. Overfitting,
Yes,
when you
overfitting.
can say a model is overfitting is if training accuracy is high and
Yes,
testing
yes.
accuracy is low, you can say it is overfitting.
Okay. Yes, sir. Yes. Okay, sir. Yes, please.
Thank you, sir.
Sir, and one more doubt I have. Sometimes the examples, the data sets are if it is highly unbalanced, right? In this case, here as is shown in the code, like a 0.8, 80% for training. So what would be the case for such cases, sir? Like in what way you have to work for unbalanced data sets?
Yes, sir. In unbalanced data set, we have also some approaches. We have different approaches like oversampling, undersampling. So
Okay.
some concepts are there. Okay, there is a popular algorithm called as SMOT. SMOT means synthetic minority oversampling technique. In oversampling, what we do is generally we will have the minority data set, and we will create lots of synthetic instances, which is very close to minority instance, so that the machine learning model cannot distinguish between this is original or fake like that. Okay, so like this, we will duplicate the minority instance so that the number of majority instance and minority instance are equal. So this is one approach, but this approach will create lots of bias in the model. Okay, so to overcome the bias, what generally researchers will do is they will do instance selection processes there. Okay, so some genetic algorithms are there. For example, PSO or gray wolf optimization. So using this, they will be picking the correct instance so that the bias will not come.
Okay. Okay, sir. Sir, can you shed some light on optimization? There are different optimization we are seeing every day in some research papers. Is it
Okay.
always necessary to choose a very good optimization?
No, sir. As far as machine learning concerned, there is no particular rule that this has to be done, this has to be done. For example, even feature selection also, there is no rule that feature selection should be done. The success of machine learning model is try and error method only. So
Okay.
for example, in this, we have included all the features. We will try the model. If the accuracy is being satisfied by us, we can leave like that only. Suppose
Okay.
if we are not able to, we are not satisfied, then we can do feature selection, or we can go for hyperparameter tuning, or we can
Okay.
use some genetic algorithms, or we can use for ensemble learning.
Okay.
So all these approaches by try and error model only we have to do. There is no common template is not there. First we have to do this, second we have to do this like this. So because in one data set it may be successful, but there is no generalized thing.
Okay, sir. Okay, sir. Yeah, thank you, sir. Thank you. Very clear.
Thank you. Any other queries?
If you have any queries, please post in the chat box too. Okay, sir. Thank you very much for helping us with this session, for the session 6. Thank you very much. The feedback
Thank
link
you.
will be posted. Yes, sir. Thank you very much.
Thank you, sir. Thank you, sir.
Thank you. Thank you. It's very clear and very informative, sir. Particularly the demo you showed, coding is quite interesting, and we could have grasped. So, you were using Kaggle, sir. Am I right? The demo you showed in Kaggle.
Yes, sir. Yes, sir.
Okay.
Kaggle, actually, I have done some pre-processing before this because only
Okay.
small time is there.
Yes. Yes. Yes.
So pre-processing I have done before itself.
Okay. Okay, sir. Fine, sir. Thank you very much for handling
Thank
this
you, sir.
session, sir. Thank you.
Thank you
Thank you.
all. Thank you.
Yes. Thank you, sir.